The subcategory fluid mechanics is defined as a science that deals with the behavior of fluids at rest, fluid statics or in motion, fluid dynamics, and the interaction of fluids with solid or other fluids at the boundaries. The study of fluids at rest is called fluid statics. The study of fluids in motion where pressure forces are not considered is called fluid kinematics, and if the pressure forces are also considered in the fluid in motion, that branch of fluid is called fluid dynamics. Fluid mechanics itself is also divided into several categories. The study of motion of fluid that are practically incompressible, such as fluids, especially water and gases at low speed, is usually referred to as hydrodynamics. A subcategory of hydrodynamics is hydraulics, which deals with liquid flow in pipes and open channels. Gas dynamics deals with the flow of fluids that undergo significant density changes, such as flow of gases through nozzles at high speed. The category of aerodynamics deals with flow of gases, especially air, over bodies such as aircraft, rockets, and automobiles at higher or lower speed. Some of the other specialized categories are meteorology, oceanography, and hydrology deal with naturally occurring flow. What is fluid? A substance that exists in three primary phases: solid, liquid, and gas. A substance in liquid or gas phase is referred to as fluid. Distinction between a solid and a fluid is made on the basis of substance's ability to resist an applied shear or tangential stress that tend to change its shape. A solid can resist an applied shear stress by deforming, whereas a fluid deforms continuously under the influence of shear stress, no matter how small. In solid, stress is proportional to strain, but in fluid, stress is proportional to strain rate. What is fluid? When a constant shear force is applied, a solid eventually stops deforming at some fixed strain angle, whereas fluid never stops deforming and approaches a certain rate of strain. In a liquid, molecules can move relative to each other, but the volume remains relatively constant because of the strong cohesive force between the molecules. As a result, liquid takes shape of the container it is in, and it forms a free surface in a large container in a gravitational field. A gas, on the other hand, expands until it encounters the wall of the container and fills the entire available space. This because gas molecules are widely spaced and cohesive force between them are very small. Unlike liquid, gases cannot form a free surface. There is a wide variety of fluid flow problems encountered in practice, and it is usually convenient to classify them on the basis of common characteristics to make it feasible to study them in groups. Viscous versus inviscous regions of flow. When the two fluid layers are relative to each other, a friction force develops between them, and the slower layer tries to slow down the faster layer. This internal resistance to flow is quantified by fluid property viscosity, which is a measure of internal stiffness of the fluid. Viscosity is caused by cohesive force between the molecules in liquid and by molecular cohesion in gases. Molecular collisions in gases. There is no fluid with zero viscosity, and thus all fluid flows involve viscous effect in some degree. Flows in which the frictional effects are significant are called viscous flow. However, in many flows of practical interest, there are regions, typically regions not close to solid surfaces, where viscous forces are negligibly small compared to inertial or pressure forces. Neglecting the viscous terms in inviscid flow regions greatly simplifies the analysis, without much loss in accuracy. Internal versus external flow. A fluid flow is classified as being internal or external depending on whether the fluid is forced to flow in a confined channel or over a surface. The flow of an unbound fluid over a surface such as plate or wire or pipe is external flow. The flow in a pipe or duct is internal flow if the fluid is completely bounded by solid surfaces. Water flow in a pipe, for example, is internal flow, and air flow over a ball or over an exposed pipe during a windy day is external flow. Compressible versus incompressible flow. A flow is classified as being compressible or incompressible depending on the level of variation of density during flow. Incompressibility is an approximation, and flow is said to be incompressible if the density remains nearly constant throughout. Therefore, the volume of every portion of fluid remains unchanged over the course of its motion. When the flow or the fluid is incompressible, The densities of the liquid are essentially constant and thus the flow of liquids are typically incompressible. Therefore, liquids are usually referred to as incompressible substance. Compressible versus incompressible flow. A pressure of 210 atm, for example, causes the density of liquid of water at 1 atm to change by just 1%. Gases, on the other hand, are highly compressible. A pressure change of just 0.01 atm, for example, causes change of 1% in the density of atmospheric air. Laminar versus turbulent flow. Some flows are smooth and orderly while others are rather chaotic. The highly ordered fluid motion characterized by a smooth layer of fluid is called laminar. The flow of high viscosity fluids such as oil at low velocities is typically laminar. The highly disordered fluid motion that typically occurs at high velocities and is characterized by velocity fluctuation is called turbulent flow. The flow of low viscosity fluids such as air at high velocities is called turbulent flow. A flow that alternates between being laminar and turbulent is called transitional flow. The term steady and uniform are frequently used in engineering and thus it is important to have clear understanding of their meaning. The term steady applies no change at a point with time. The opposite of steady is unsteady. The term uniform applies no change with location over a specified region. Any characteristics of a system is called property. Some familiar properties: pressure, temperature, and volume and mass. Other less familiar properties include viscosity, thermal conductivity, modulus of elasticity, thermal expansion, coefficient of electric resistivity, and even velocity and elevation. Properties are considered to be either intensive or extensive. Intensive properties are those that are independent of mass of a system, such as temperature, pressure, and density. Extensive properties are those whose values depend on size or extent of the system. Total mass, total volume, and total momentum are some examples of extensive properties. Properties of the fluid. An easy way to determine whether a property is intensive or expansive is to divide the system into two equal parts with an imaginary portion. Each part will have the same value of intensive property as original system but half the value of extensive property. Density or mass of a fluid is defined as the ratio of mass of a fluid to its volume. Thus, mass per unit volume of a fluid is called density. It is denoted by symbol rho. The unit of mass density is SI is kg per cubic meter, kg per meter cube. The density of liquid may be considered as constant while that of gases changes with variation of pressure and temperature. Mathematically, mass density is written as rho is equal to mass of fluid by volume of fluid. Viscosity is defined as the property of fluid which offers resistance to the motion of one layer of fluid over another adjacent layer of the fluid. When two layers of a fluid a distance of dy apart move over one another at different velocities, say u and u plus du as shown in plus du, the viscosity together with relative velocity causes a shear stress acting between the fluid layer. The top layer causes a shear stress on the adjacent lower layer, while the lower layer causes a shear stress on the adjacent top layer. This shear stress is proportional to the rate of change of velocity with respect to y. It is denoted by symbol tau called mathematically tau is directly proportional to du by dy, or tau is equal to mu du by dy, where mu is the constant of proportionality and is known as the coefficient of dynamic viscosity or only viscosity. Du by dy represents the rate of shear strain or rate of shear deformation or velocity gradient. From the equation we have mu is equal to tau divided by du by dy. Thus, viscosity is also defined as the rate of shear stress required to produce unit rate of shear strain.